In this lesson, we will review some descriptive statistics, including measures of center, measures of spread, and measures of position. We'll also touch on the types of associations between variables and how to measure linear correlation. Let's start our review with measures of center. The mean of a dataset measures the center by summing all data values and dividing that sum by n, the number of data values. If we think of all data values as weights, then the mean is the value which balances them. The population mean is denoted by mu. This is the mean of the entire population. It is often approximated by the mean of a sample from that population, which is denoted by x bar. The median is also a measure of center, but it measures the center in a different way. The median divides a dataset into approximately two equal pieces, so that half of the values are above the median and half are below it. When the mean and median of a dataset are approximately the same, we can generally expect that the dataset is approximately symmetric. If the mean is significantly greater than the median, this generally indicates that the dataset is skewed to the right. And if the mean is significantly less than the median, this generally indicates that the dataset is skewed to the left. Sometimes it is useful to divide a dataset into more than two pieces. We do this with what's called a measure of position, the quartiles. Quartiles divide a dataset into four approximately equal pieces. For example, suppose that we know that the third quartile of the lifespan of a certain type of goldfinch is approximately 72 months. This means that 75% of this type of goldfinch do not live for more than 72 months. Alternatively, we could say that 25% do live longer than 72 months. A dataset can be divided further. Percentiles divide a dataset into hundredths. For any number p between 1 and 99, the pth percentile separates the lowest p% of the data from the highest 100 minus p%. As we can see, the 25th percentile is the same as the first quartile. The 50th percentile is the same as the second quartile, which is the same as the median. And the 75th percentile is the same as the third quartile. Percentiles can be a useful way of describing data. For example, the World Health Organization keeps data on weights based on infant age. Using percentiles, the weight of a particular infant can be compared to those around the world to determine whether the weight falls into a usual range. Let's talk about measures of spread. Take a look at the average monthly temperatures of two locations, San Francisco and St. Louis. The mean temperatures in San Francisco is about 57.5 degrees Fahrenheit. For St. Louis, the mean temperature is about 56.1 degrees. We can see that there is not a big difference in mean temperatures for the two cities. However, a quick dot plot of the monthly temperatures shows that the St. Louis temperatures are much more spread out. So how do we measure the spread of a dataset? One measure of spread is variance. Variance measures spread by determining the average distance each data value is from the mean. The variance of a population is denoted by sigma squared. And the variance of a sample is denoted by s squared. We can see that the formulas are different depending on whether we are dealing with a population or a sample, but normally this difference is not very significant. One problem with using variance as a measure of spread is that it results in units that are hard to interpret. Because all data values are squared in the formulas, the units will be squared units. If we were to calculate the variance of the temperatures, our units would be degrees squared, which is kind of hard to get one's head around. A more common measure of spread is the standard deviation. The standard deviation is the square root of the variance. The standard deviation is more useful because the units are the same as the data. For example, hours, meters, degrees, etc. The standard deviation of a population is denoted by sigma, and the standard deviation of a sample is denoted by s. Let's talk about how to measure relationships between variables. Suppose that we have a scatter plot that shows reaction times to a stimulus by two types of mammals. We can see that larger reaction times in one mammal tend to be associated with larger reaction times in the other, which also means that smaller reaction times in one are associated with smaller times in the other. We refer to this as a positive association. In some cases, larger values of one variable are associated with smaller values of another. This is called a negative association between the variables. An example of variables with a negative association is the weight of a car and its gas mileage. Large weights are associated with smaller gas mileages, and small weights are associated with larger gas mileages. With the reaction times, the points also tend to cluster around a straight line, from lower left to upper right. We describe this by saying that the relationship between the two variables is linear. When the points do not cluster around a straight line, the relationship is nonlinear. Consider some different examples of scatterplots that exhibit various kinds of associations. When two variables x and y have a linear relationship, the strength of that relationship is measured by the correlation coefficient. A correlation coefficient is denoted by r and can be found using a somewhat complicated formula. The closer r is to 1 or -1, the stronger the linear relationship between the variables. The closer r is to 0, the weaker the relationship. Be careful though. R is only useful when measuring linear relationships. If the data are nonlinear, it does not have a meaningful interpretation. Let's click over into R and see how to calculate some descriptive measures. Okay, so here we are in R, and so we're going to work through this script. Now I'm going to load some data that I've got. So the first thing I'm going to do is call the reader package. Now I'm going to pull in a data set. Now in this data set there are two variables, chirps 2 min and temp C. Chirps 2 min is the number of cricket chirps recorded over a 2-minute period, and temp C is the temperature in Celsius of the location where the observations were made. Now in the previous lesson, we saw how to pull in a data set from a Dropbox. So I'm just going to pull this in, and let's take a quick look at this data set. So I can see some of my values here. Now, in order for R to be able to work with these variables, I need to attach this dataset to my workspace, and I do that with the attach command. Okay, so I've got my dataset loaded, and it's attached to my workspace. I'm going to clear out the console here, and then we'll move on with finding some descriptive statistics. The summary command returns the mean and median, all quartiles, and the maximum and minimum for all variables. So I'm going to run the summary command on this dataset that I pulled in. And remember, this dataset includes two variables, so it will return the statistics for both variables. Okay, we see that for both variables we have the minimum, the first quartile, the median, the mean, the third quartile, and the maximum. Now, one thing I think you should get in the habit of is drawing out whatever information you can. For example, take a look at the temp C statistics here. Note how the mean and median are very close to each other. Now from this, we can guess that the temperature data are probably pretty symmetric. Now the summary command can be used for individual variables. For example, we could run it on just the chirps 2 min variable. And we see we get the minimum, the first quartile, the median, the mean, the third quartile, and the maximum just for that variable. Now it may be that we just want the mean and median of a data set. The mean is found with the mean command. So the mean of the chirps 2 min variable is 235.57. The median command returns, well, the median. The median temperature is 19.86 degrees Celsius. Similarly, we have a var command, which returns the variance, and an sd command, which returns the standard deviation. Let's find the variance of the chirps 2 min variable. And so we find the variance. The standard deviation is found with the sd command, and remember that would just be the square root of the variance. We find the standard deviation to be 67.59285. Now more graphical displays will be presented in the next lesson, but let's do a simple one. The plot command returns a scatter plot between two variables. So I'm going to do a scatter plot here between the temperature C and the chirps to min variable. Now don't worry about this other option here, the PCH equals 16. All that option is doing is saying which symbol I should use in my scatter plot. So let's take a look at this. Now we can see here that as the temperatures tend to rise, the number of chirps every 2 minutes tends to rise as well. Not only that, but they seem to cluster around a straight line. So we can describe the relationship between these two variables as a positive linear association. Now since we have a linear relationship here, we know that the correlation coefficient will measure the strength of it. In R, we can find the correlation coefficient using the COR command. And we find the correlation coefficient to be 0.9605928. Okay, so that's it for this lesson. Best of luck as you move forward.